For generations, Owens Lake stood as one of the starkest reminders of how dramatically a landscape can change when water disappears. Located in eastern California between the towering Sierra Nevada and the rugged Inyo Mountains, the basin was once a vast inland lake that endured for hundreds of thousands of years. Then, within little more than a decade, it vanished. In the years that followed, the dry lakebed became infamous across the United States for producing immense dust storms that carried toxic particles across communities, highways, and military facilities. Air pollution levels reached records unmatched anywhere else in the nation. Residents endured hazardous conditions, public agencies struggled to contain the problem, and the exposed lakebed became synonymous with environmental decline. Yet today, a remarkable transformation is unfolding across the same landscape. Shallow waters shimmer across portions of the basin. Migratory birds gather in astonishing numbers. Wetland habitats have emerged where blowing dust once dominated. A place once known primarily for environmental damage is increasingly recognized for ecological recovery. The change did not begin as a wildlife restoration effort or a grand conservation program. It began as a practical response to one of the worst air quality crises in American history. Owens Lake occupies a broad depression in eastern California near the base of some of the highest mountains in the continental United States. Long before modern cities, highways, or aqueducts existed, the basin contained a large saline lake fed primarily by the Owens River. For approximately 800,000 years, water flowed into the lake, creating an inland sea covering roughly 100 square miles, or about 259 square kilometers. Although relatively shallow compared with many major lakes, Owens Lake played an important role in the regional environment. Water arriving from snowmelt in the Sierra Nevada sustained the lake while evaporation concentrated minerals over vast stretches of time. The result was a unique aquatic ecosystem surrounded by one of California's most dramatic mountain landscapes. During the late 19th century, the lake also supported economic activity. Steamships crossed its waters, carrying cargo associated with mining operations in the region. Communities developed along the shoreline, benefiting from transportation links and access to water. Settlements such as Keeler became important local centers connected to the lake's presence. Everything changed during the early 20th century. Southern California was expanding rapidly. Los Angeles required new water supplies to sustain population growth and economic development. Engineers and planners identified the Owens Valley as a source capable of supporting the city's future needs. Construction of the Los Angeles Aqueduct created one of the most ambitious water infrastructure projects of its era. Completed in 1913, the aqueduct redirected water from the Owens River and transported it approximately 233 miles, or about 375 kilometers, southward toward Los Angeles. The consequences for Owens Lake became visible almost immediately. Without its primary source of inflow, the lake began shrinking. Shorelines retreated, water levels dropped steadily year after year. By the mid-1920s, only about 13 years after major diversions began, the lake had effectively disappeared. A landscape that had held water for hundreds of thousands of years became a dry basin in little more than a decade. The disappearance of the lake did not simply leave behind an empty depression. It exposed a vast lakebed containing mineral deposits accumulated through countless cycles of evaporation. Those deposits would eventually create an environmental challenge unlike anything previously encountered in the United States. Many dry lakebeds develop hard crusts capable of resisting erosion. Owens Lake followed a different path because of its distinctive chemistry. Over immense spans of time, runoff from surrounding mountains carried dissolved minerals into the basin. As water evaporated, minerals remained behind and became increasingly concentrated. The resulting deposits included large amounts of sodium carbonate and sodium sulfate. Unlike ordinary table salt, these compounds often produced fragile, powder-like surfaces rather than durable crusts. Even after the lake vanished, groundwater remained relatively close to the surface in many areas. Moisture migrated upward through sediments and evaporated at the surface. Every cycle left additional mineral deposits behind. Seasonal weather intensified the process. Crystals formed, expanded, fractured sediments, and eventually broke down into fine particles. The exposed lakebed essentially became a factory for dust production. Strong winds frequently sweep through Owens Valley. Geography amplifies their power. Air moving between the Sierra Nevada and the Inyo Mountains accelerates through the corridor, increasing its ability to lift and transport particles. Once winds reached the lakebed, they encountered an enormous supply of loose material. Fine dust rose into the atmosphere and traveled far beyond the basin itself. Some particles were microscopic, small enough to remain suspended in the air for extended periods. Others contained trace elements that raised concerns about human health and environmental quality. The scale of the problem became increasingly difficult to ignore. Communities downwind experienced repeated dust events. Residents reported respiratory difficulties and reduced visibility. Roads became hazardous during severe storms. Drivers along major transportation routes sometimes encountered conditions resembling dense fog, except the obscuring material consisted of airborne dust. Public health concerns intensified as monitoring efforts expanded. Researchers and regulators documented particulate concentrations far exceeding federal standards. At times, pollution measurements reached levels unprecedented within the United States. Owens Lake gradually earned a reputation as the nation's largest single source of particulate air pollution. The numbers illustrated the severity of the situation. Each year, tens of thousands of tons of dust entered the atmosphere from the exposed lakebed. Pollution events repeatedly exceeded regulatory thresholds established to protect public health. The problem persisted decade after decade, becoming one of California's most challenging environmental management issues. Responsibility for addressing the dust became the subject of prolonged legal and regulatory disputes. Local air quality authorities argued that the lakebed's condition resulted directly from historic water diversions. Los Angeles, meanwhile, maintained that many of the actions responsible for the lake's disappearance occurred long before modern environmental regulations existed. Years of legal proceedings followed. Eventually, regulatory agencies secured agreements requiring Los Angeles to implement large-scale dust control measures. The city accepted responsibility for funding and operating an extensive program designed to reduce emissions from the lakebed. The undertaking would become one of the largest environmental engineering projects ever attempted in North America. Beginning around the start of the 21st century, construction crews, engineers, planners, and environmental managers transformed significant portions of the basin into a carefully controlled dust suppression system. The objective was straightforward: stop the dust. There was no requirement to recreate the original lake. No mandate existed to restore historical ecosystems. The focus centered almost entirely on air quality compliance. Several different techniques were employed. One approach involved shallow flooding. Water was distributed across broad sections of the lakebed using an elaborate network of infrastructure. Low earthen berms divided the surface into numerous cells, allowing managers to regulate water depth and movement with precision. The water layers remained relatively shallow. Their purpose was not to create deep lakes or permanent reservoirs. Instead, they prevented the formation of fragile salt surfaces vulnerable to wind erosion. Another method relied on vegetation. Specialized salt-tolerant plants were established in selected areas. These species could survive under highly saline conditions while helping stabilize sediments. Their roots anchored the soil, while stems reduced wind velocity near the surface. Additional sections received gravel coverings. Layers of coarse material created protective barriers separating sediments from atmospheric processes responsible for dust generation. In these locations, dust suppression occurred without continuous water use. Together, these methods formed an immense engineered landscape stretching across dozens of square miles and many tens of square kilometers. The project required enormous investment. Over time, expenditures climbed into the billions of dollars. Infrastructure expanded across the basin. Monitoring systems tracked environmental performance. Maintenance operations became a permanent component of managing the lakebed. Results began appearing. Dust emissions declined dramatically. Measurements that once shattered national records dropped sharply. Air quality improved across much of the region. The frequency of severe pollution events decreased. Regulatory targets increasingly came within reach. From a technical perspective, the project succeeded in accomplishing its original mission. Yet another development was quietly unfolding at the same time. Water was returning to portions of Owens Lake, not enough to restore the ancient inland sea, but enough to create something unexpected. Life began responding almost immediately. Shallow flooded cells exposed to sunlight developed conditions favorable for microscopic algae. Nutrient-rich environments emerged across portions of the managed wetlands. Biological activity expanded rapidly. The appearance of algae created new food resources. Soon insects arrived. Among the most notable were alkali flies, species uniquely adapted to saline environments. Their populations expanded as food sources became available. Larvae thrived in shallow waters while adults emerged in enormous numbers. What might seem like a minor ecological change carried major consequences. Insects attract birds. Owens Lake occupies a strategic location along the Pacific Flyway, one of the most important migratory bird routes in the Western Hemisphere. Every year, countless birds travel between northern breeding grounds and southern wintering areas. Migration demands energy. Birds require places to rest, feed, and recover during long journeys. Historically, Owens Lake had provided such habitat before its disappearance during the 20th century. Now, portions of that opportunity were returning. As insect populations expanded and shallow waters spread across managed areas, birds began appearing in increasing numbers. At first, the arrivals were modest, then flocks grew larger. Before long, the lakebed was attracting remarkable concentrations of migratory species. Shorebirds found extensive feeding grounds along the edges of shallow ponds. Waterbirds utilized open flooded areas. Species adapted to saline wetlands discovered suitable habitat across sections of the basin. Observers documented avocets, stilts, sandpipers, grebes, ibis, and numerous other species using the restored environments. The scale of usage surprised many who had viewed the project solely through the lens of air quality management. Surveys eventually recorded well over 100,000 birds utilizing the area during migration periods. A place long associated with dust storms had become one of the most important stopover locations in the region. Ironically, the engineering features designed for operational efficiency helped create valuable habitat. Thousands of berms divided the lakebed into geometric cells. From above, the arrangement resembled a vast grid stretching across the desert. For birds, however, those structures created extensive shoreline environments. Shorelines represent highly productive ecological zones. They provide access to food resources concentrated where water meets land. By increasing the amount of edge habitat, the engineered design unintentionally enhanced conditions for many species. The landscape looked artificial from satellite imagery. Rectangles, straight lines, maintenance roads, and carefully managed water levels dominated the view. Yet wildlife responded not to aesthetics, but to ecological opportunity. Food existed, water existed, resting areas existed. That combination proved sufficient. Recognition of the area's ecological importance expanded as monitoring continued. Conservation organizations began documenting the growing significance of Owens Lake for migratory birds. The site gained increasing attention as a habitat supporting large numbers of shorebirds traveling along continental migration routes. The transformation extended beyond seasonal visitors. Some species began nesting within the managed environment. Among the most notable was the western snowy plover, a bird of conservation concern in California. Breeding activity demonstrated that the habitat provided more than temporary stopover opportunities. Birds were establishing territories and raising young. That development introduced new dimensions to management decisions. A project initially created to control dust now supported protected wildlife resources. Air quality objectives remained central, but habitat considerations became increasingly important as ecological value expanded. Managers faced a complex balancing act. Water remained essential for many habitat functions. At the same time, water represents a highly valuable resource throughout California, especially during drought periods. Every acre of shallow flooding requires ongoing supplies. Maintaining wetlands consumes water that might otherwise remain available for urban use, agriculture, or environmental needs elsewhere. Consequently, some areas have gradually shifted toward alternative dust control methods requiring less water. Gravel surfaces and other techniques offer advantages in terms of conservation. However, they generally provide fewer ecological benefits than flooded habitats. The future configuration of Owens Lake therefore depends on continuing decisions about resource allocation, environmental priorities, and long-term sustainability. Climate conditions add another layer of uncertainty. Snowfall in the Sierra Nevada strongly influences water availability throughout the region. Variations in precipitation, temperature, and runoff affect supplies entering the broader system. Periods of drought place additional pressure on water resources. Managers must continually evaluate how best to balance air quality requirements, habitat preservation, and water conservation objectives. Despite those challenges, the achievements already visible across Owens Lake are extraordinary. Few places in the United States have undergone such dramatic environmental transitions within a relatively short period. An inland sea that existed for approximately 800,000 years disappeared in about 13 years. Its dry lakebed then generated some of the most severe particulate pollution ever measured in the nation. After decades of environmental degradation, a multi-billion-dollar engineering effort successfully reduced dust emissions and improved air quality. Along the way, an unexpected ecological revival emerged. Algae colonized shallow waters, insects multiplied, birds returned in huge numbers. Protected species established breeding populations. Internationally significant habitat developed across a landscape never intended to become a wildlife sanctuary. The sequence illustrates a broader reality often observed in environmental systems. Nature frequently responds rapidly when essential conditions reappear. Water returned to portions of Owens Lake because engineers needed to suppress dust. Yet once moisture reached the basin, biological processes resumed with remarkable speed. Organisms adapted to saline environments reoccupied available habitat. Food webs developed. Ecological interactions expanded. The outcome was neither fully planned nor entirely predicted. It emerged from the intersection of environmental management and natural adaptation. Today, Owens Lake remains unlike the inland sea that existed before the aqueduct era. The original lake has not returned. Vast portions of the basin remain dry. Industrial infrastructure continues operating across the landscape. Yet the image of Owens Lake as merely a barren dust source no longer reflects reality. Across sections of the former lakebed, shallow wetlands support thriving biological communities. Migratory birds descend upon waters that did not exist a generation ago. Air quality conditions have improved dramatically compared with the worst years of the dust crisis. The basin that once symbolized one of California's most severe environmental failures now stands as evidence that damaged landscapes can evolve in unexpected directions. Owens Lake's modern identity is shaped by contrasts: ancient water and modern engineering, environmental loss and ecological recovery, dust suppression infrastructure and internationally recognized bird habitat. The transformation continues, influenced by water availability, climate conditions, management choices, and natural processes that remain active across the desert floor. For much of the 20th century, Owens Lake was known primarily as America's deadliest dust zone. In the 21st century, increasing numbers of visitors, scientists, conservation groups, and environmental managers see something else emerging across the same landscape. Not the return of the original inland sea, but the rise of a functioning oasis, where wildlife, water, and engineered solutions now coexist in one of California's most remarkable environmental turnarounds. Even as the transformation continues, the story of Owens Lake remains deeply tied to the geography that first created both its abundance and its problems. The basin sits within a dramatic corridor of mountains, where elevation changes occur over relatively short distances. To the west, the Sierra Nevada rises sharply, with peaks exceeding 14,000 feet, or more than 4,260 meters. To the east, the Inyo Mountains form another imposing barrier. Together, these mountain ranges shape weather patterns, influence wind behavior, and control the movement of water throughout the valley. For thousands of years, seasonal snow accumulating in the Sierra Nevada acted as a natural reservoir. Each spring and summer, melting snow fed streams and rivers that carried water into Owens Valley. The Owens River eventually delivered that water into Owens Lake, maintaining the balance between inflow and evaporation. Because the region is naturally arid, evaporation was always a powerful force. Minerals gradually accumulated as water disappeared into the atmosphere, creating the saline conditions that characterized the lake long before modern development arrived. When the lake vanished during the 20th century, those same geological and climatic characteristics became factors in the dust crisis. The enclosed basin trapped vast mineral deposits, while the mountain corridor accelerated winds capable of lifting fine particles high into the atmosphere. The problem was not simply the existence of a dry lakebed. It was the combination of unique mineral chemistry, persistent groundwater movement, and regional wind patterns that turned Owens Lake into such an extraordinary source of airborne dust. Today, those natural forces still operate, but they interact with a landscape that has been extensively engineered. Water distribution networks, monitoring stations, pumps, channels, and containment structures form part of a complex system designed to keep dust emissions under control. Maintaining that system requires constant attention. Water levels must be monitored carefully. Vegetation requires management. Infrastructure must withstand extreme temperatures, strong winds, and highly saline conditions that can accelerate wear and corrosion. The scale of the operation often surprises people unfamiliar with the region. Dust control at Owens Lake is not a one-time project that was completed and forgotten. It functions more like a permanent environmental management program. Crews continuously inspect conditions across large sections of the basin, ensuring that surfaces remain stable and that regulatory requirements continue to be met. Without that ongoing effort, the dust problem could quickly re-emerge. At the same time, the ecological benefits generated by the project have become increasingly difficult to separate from the original air quality mission. Every migration season brings renewed evidence of how valuable the habitat has become. Birds traveling along the Pacific Flyway encounter a landscape offering food, water, and resting areas within a region where such resources are often limited. For many species crossing the interior west, these wetlands provide an important refuge during journeys spanning thousands of miles and thousands of kilometers.